Okay, so in this video, what I wanted to present is why do we need phasors when we analyze AC circuits? So I think that it is better to start by considering the following circuit. Imagine that you have a voltage source, okay, and this voltage source has the behavior of a sinusoid, okay, that is Vm times the cosine of omega times t plus theta. Okay, and we connect to this voltage source a resistor. Okay, and this resistor has a resistance R. Also, we have an inductor that has an inductance L, and we have a capacitor. And this capacitor has a capacitance C. Okay, and let's assume that the current goes in this direction and that the voltage of the resistor has the following polarity. The voltage of the inductor has the following polarity, and the voltage of the capacitor has the following polarity. Okay? And based on this information, I want to analyze this circuit and compute, let's say, the voltage of the capacitor. Remember that the inductor and the capacitor are devices or are electrical devices that can storage energy. In particular, the inductor can storage energy in the form of current. Okay? So the inductor can storage energy in the form of current, and the voltage can storage energy in the form of voltage. Okay? So these are the main two components that we want to consider. Moreover, it is important that we mention that the voltage in the inductor is determined by the inductance value times the derivative of the current that passes through the inductor with respect to time. And the voltage of the capacitor is equal to 1 over C, where C is the capacitance value, times the integral of the current with respect to time. Okay? This inductance value has units of Henrys, okay, often denoted by the letter H, and the capacitance has units of farads, often denoted by the letter F. So here we have the Henrys of the inductance that are denoted by the letter H, and here we have the capacitance of the capacitor denoted by the letter F, referring to farads. Okay, so we have all these two components, and now one of the things that we want to analyze is the voltage of the capacitor. Okay, so to analyze the voltage of the capacitor, we need to apply the Kirchhoff voltage law. Okay, so remember that in order to establish the Kirchhoff voltage law, the Kirchhoff voltage law states that the addition of each of the voltages in a circuit within a loop or in a closed loop should be equal to 0. So here you need to add the voltage of the capacitor, the voltage of the resistor, the voltage of the inductor, and the voltage of the capacitor in order to define the Kirchhoff voltage law. So here, since we are considering that the current goes in this direction, we can say that the Kirchhoff voltage law is as follows. We have Vm times the cosine of omega times t plus theta plus Vr plus the voltage of the inductor plus the voltage of the capacitor. And the additional of all of these four voltages is equal to 0. Okay? Now remember that the voltage of the resistor is equal to the resistance value times the current, okay? And that the voltage of the inductor is given by this expression and the voltage of the capacitor is given by this expression. So I can substitute all of these values into this expression. So we have minus Vm times the cosine of omega times t plus theta, and we have the voltage of the resistor that is equal to R times I, that is the value of the current that is in this circuit, plus the voltage of the inductor, that is equal to L times the derivative of the current with respect to time. And also we have the voltage of the capacitor. But since I want to compute the voltage of the capacitor, I will leave this term as it is, okay? And this is equal to 0. Now, we have here the current. So what I can do is to substitute the value of the current based on the relation of the capacitor. I can do this because I know that this is a series circuit. So remember that for a series circuit, the current is preserved for each of the elements. So the current that flows through the resistor is the same current that flows through the inductor, and also is the same current that flows through the capacitor. So if I solve this equation for the current, I can express all the equation in terms of the voltage of the capacitor, that is my variable of interest. So if I solve this equation for the current, we have that the current is equal to C times the derivative of the voltage of the capacitor with respect to time. Okay? So this is the current that passes through the capacitor, but the current that passes through the capacitor is the same current that passes through all the elements in this circuit. So now what I can do is to express the following. We have Vm times the cosine of omega times t plus theta plus r times the current, but the current is equal to this value. So we have C times the derivative of the voltage of the capacitor with respect to time plus L times the derivative of the current. But we know that the derivative of the current, that the current is equal to this expression, so I can substitute that value here. So we have that the derivative of the current with respect to time. Here we have the value of the current, that is C times the derivative of the voltage of the capacitor with respect to time, plus B plus the voltage of the capacitor, and this is equal to 0. Now, you can see here that things start to get a little bit complicated, but because we have here a double derivative, and here we have a derivative also. I can simplify this a little bit further. We have minus Vm times the cosine of omega times t plus theta plus r times c times the derivative of the voltage of the capacitor with respect to time plus L times C. I can extract the C value of this constant term out of the derivative because it is a constant. And I will have that the derivative of the voltage of the capacitor with respect to time becomes a double derivative. Okay, because the only thing that changes with time is the voltage of the capacitor in this expression. Plus the voltage of the capacitor, and this is equal to 0. So the challenging part here is that, well, in order to determine the voltage of the capacitor, I need to solve this differential equation. And this is not a simple differential equation because we have this input source or this input voltage source that has this behavior. I need to compute or solve by considering that. And also we have a second order differential equation because of this term. And this can get complicated. In fact, one way in which you can solve this differential equation is using the Laplace transform. Okay? You can solve this using the Laplace transform. Okay? But this can be very challenging. In fact, well, it is not too complicated. You can solve all of this using the Laplace transform. But the problem is that, well, here we are analyzing like the most basic circuit. That is an RLC circuit that is in series. But imagine that you have multiple meshes or multiple loops or multiple nodes in your circuit. Well, you will have more than one differential equation. You will have more than 2 or 3 differential equations that have this structure. So you need to solve all these differential equations, not only correctly, but simultaneously. And that can be very complicated, okay? So instead of working with the sinusoidals and also with derivatives, one of the things that we can do is to transform all these sinusoidals and also these derivatives and convert them into a representation that is more easy to manage. And also we can solve this equation algebraically. Okay. So one way to do that is to introduce the idea of a phasor. Okay. So what is a phasor? I think that is important to mention. The phasor is basically a transformation. In fact, we call it a frequency domain transformation or representation in which we can convert a sinusoid into a complex number by considering only the amplitude of the sinusoidal and the phase angle. Okay, so in order to do that, let's consider the following expression. In fact, we have this expression for our voltage source. So we can say that Vm times the cosine of omega t is the value for voltage source. Okay, now I will take the amplitude and I will take the argument of this sinusoid, and I will plug in these values into the expression of the Euler's identity, okay, or the so in order to do that, we have here Vm times E elevated to the J times omega times t plus theta, okay? And by Euler's identity, I know that this complex exponential is equal to Vm times the cosine of omega times t plus theta plus j times the sine of omega times t plus theta. Okay? And if you look into this expression, this Euler's identity, you can notice that the real part of the Euler's identity is equivalent to the sinusoid that I have originally. Okay? So I can express this complex exponential as follows. I can say that Vm times the cosine of omega times t plus theta is equal to the real part of Vm times e elevated to the j times omega times t plus theta. Okay? And because as you can see here, the real part of this complex exponential is equivalent to my original sinusoid. But another thing that I can do is to say, okay, I can distribute the terms of this exponential. So I will have that this expression is equal to the real part of Vm times E elevated to the J times omega times T times E elevated to the J times theta. Okay. And now, um, what I can do and what we call a phasor is that, well, instead of working with all these trigonometric function, I will define my phasor as follows. So first, I would like to define this trigonometric function as bt, b that depends on time, is equal to this expression, okay? And a phasor is often denoted by a capital letter. In this case, I am using the capital letter for B, that is equal to the this value that is Vm, that is the amplitude of my original sinusoidal, and I will express this phasor in polar form, okay? And the angle of this polar form is this angle theta, that is essentially the phase angle of my sinusoidal. Okay, so essentially what we call a phasor is only taking this complex number, and we are getting rid of this term. Okay, we are not using this term that contains the variable t and the frequency of the sinusoidal, that is omega. We can remove that and only work with the amplitude of my sinusoidal and the phase angle expressed as a complex number. Okay, and the reason in which we can do that, or the reason why we can do that in the first place, is that we can avoid using this complex exponential that depends on time, because this complex exponential that depends on time introduces all these complexities into my analysis. Okay, and I can avoid computing or using this term in my calculation and only working with this complex number because Vm times E elevated to the j times theta, that I can express it as follows. Now I will write it right here in order to be clear. E is equal to Vm times E elevated to the j times theta is basically the exponential representation of a complex number, and this is the polar representation. But the interesting part is that I can avoid all this term, okay, in particular, because all my elements in my circuit, that is, not only the voltage source, but also the resistor, the inductor, and the capacitor, operate at the same frequency. So I can avoid the use of this term because all my elements will operate at the same frequency. So what I can do is to work with this complex number, this expression, and at the end, what I can do is to only multiply all my results by this term because I am imposing the condition that all the elements in my circuit will operate at the same frequency. And in most of the cases, that condition holds, okay? And that is very useful because instead of working directly with this complex exponential, what I can do is to work with this complex number, that is Vm times E elevated to the j times theta, that I can express in polar based on this expression, and I can work with a complex number instead of working directly with the sinusoidal, because I know that the real part of this complex number multiplied by this term will be equal to my sinusoidal, my original sinusoidal. So I can convert or return to my original representation by considering these facts. In fact, you will notice that the conversion between phasor to the time domain or from my original function to the phasor representation is very simple. There are certain conditions that we need to be careful about, but this property will allow us to convert the original differential equation that is right here and convert it to only numbers. And we can solve this differential equation algebraically. Okay, that is the main goal of all this analysis. Okay, and this is essentially the phasor. Okay, well, so as an example, no, in order to see how you can convert these sinusoidals into a phasor, what we can do is the following. Let me write an example. Well, another condition that we must meet is that the original trigonometric function must be expressed as a cosine. So this phasor transformation only works with cosine functions. So if you have a sine wave, you need to convert this sine wave into a cosine wave in order to convert it to a phasor. So let's make an example. For instance, here we have the following sinusoidal. We have 4 times the cosine of omega times t plus 50 degrees, okay? So remember that the phasor is only taking the amplitude of the sinusoidal and the phase angle and express this as a complex number. So here we have 4, that is the amplitude, and the angle is the phase angle, that is 50. Okay, so this is my phasor of this function. But I can do the same for other exercise. For instance, imagine that you have 16 times the sine of omega times t minus 30 degrees. And I can compare this sine to a phasor, but first I need to convert this trigonometric function into a cosine. So to do that, remember that I can subtract minus 90 degrees to the argument in order to convert it to a cosine. So we will have 16 times the cosine of omega times t minus 30 degrees minus 90 degrees. So this will be equal to 16 times the cosine of omega times t, okay, minus 120 degrees. And now I can express it as a phasor. We have 16 with an angle of minus 120 degrees. Okay, and this is the phasor. Okay, and I can represent all these phasor represent or have all the information that I need in order to solve the circuit. Okay, because the frequency in all the elements will be the same. So this is very useful, or a very useful transformation, and you can see that the conversion is a little bit simple. The only trick is that you need to have a positive amplitude cosine, and also, needs to be a positive amplitude cosine wave. Okay, that is the condition. We need to have a positive amplitude cosine. Okay, and I think that's it for all this video. I hope you like it, and if you have some question, you can leave a comment. So thank you very much.